All right, folks, today we're going to talk about scaling functions. Okay, so that's a multiplication factor. We're going to talk about first applying this to the function y equals x squared. So what I'm going to have you do here is list 5 points that appear on y equals x squared. You can pick whatever x values you want, and then you'll just square them. Then you're going to complete your second table so that the x values from your original are doubled and the y values are tripled. So that just takes all your x values times 2 and all your y values from the table and times 3. And when you're done with that, your task is to come up with the equation that fits the second table's points. Okay, so I'm going to let you pause the video here, and I want you to see if you can come up with an equation that works with your points. You'll know it's correct if you can plug in the x value you got here, and it comes out to that y value. Okay, so pause the video and try that for me. So I picked a couple negatives, 0, and a couple positives. So the task was to make sure that when I plugged in -4, I got a positive 12. Now this is going to relate to your note card that you have dealing with transformations of graphs, those 4 steps. But the equation that we should have come up with is y equals a 3 on the outside and a 1/2 on the inside. When we talk about transformations, just like with scale changes work a lot like translations do, in terms of what is on the inside of our grouping symbols is kind of backwards from what we think. For example, if we see an equation that said x plus 4, that would move the graph to the left 4. Similarly, if we had a -4, it would go to the right. It's backwards. We talked about this a little bit already, but when you see a 1/2 on your note card, that fits into horizontally stretched, which is a little bit backwards. So when we're doubling the x values, that really is a horizontal stretch, so we have to have a 1/2 in there to correlate with it. When we multiply our y values by 3, though, that's a vertical stretch, and what you see is what you get in front there. Of course, we always want our equations to be as simplified as possible, so this is where our 1/2 gets squared and becomes 1/4. And then now that that's 1/4 x squared, those parentheses are gone. You can actually go ahead and multiply that for a final answer of 3/4 x squared. So, kind of to show you how this works with what we've talked about with transformations of graphs and purple note card type of stuff with sentences and talking about these things. When we end up simplifying, we're only having one number, and this really says 3/4 is our vertical stretch, meaning horizontal has not happened. With that in mind, if I take this first point, so I'm just going to choose this 4, and I multiply it by that 3/4, you'll notice you get 12 over 4 is 3. -2, 3 should be on my new graph, and it is. Okay, so a couple different ways to express it, but the pattern that we need to recognize is super important. Just like when we were talking about translations, we have a rule and we have an equation. Our rule was this 2x, 3y, and just like with translation, we're going to have a name in front of it. Since we're talking about multiplication factors, that's a scale change. So we'll say the scale change on the point is 2x, 3y. Then in our equation, the first part stayed the same because that dealt with the y value, and the second part on the inside actually switched from what we saw. And we'll practice that. To begin with, we're going to look at some parent functions and rules, and we're asked to write the transformed equation, making sure it's as simplified as possible. So first up, we know we're going to put something in front and something inside, so we're going to start out with y equals, but we're going to leave some space and then write some parentheses that are pretty wide here. That gives us place to put our numbers inside and still apply our parent function to our parentheses. Now what we're going to do is start actually with the inside because I know x goes inside my grouping symbols. So the 1/2 x, when we switch what we see, changes to the reciprocal, or 2x. Then on the outside, what you see is what you get. With y, you put it directly in front. So this is the 1/3. Our job is just to simplify this. So our 2 gets squared, and that's 4x squared. Bringing down that 1/3, I know that I have one more step to simplify, just multiplying straight across there. That's 4 on top, 3 on the bottom, and x squared to finish up. Second one's no different. I know there's a negative here, but it doesn't really affect the process. We're going to start with a little bit of space out front, parentheses, because our parent function just says qubit. Then on the inside is where I start. Instead of 1/5, you should see a 5x, and then outside what you see is what you get, including that negative sign. So 5 cubed is 125. The x cubed just comes down, and then we have to multiply that by a -4. Okay, you can think about this as 4 times 100 is 400. 4 times 25 is another 100, so we've got 500 total. And then our x cubed comes down. And that's it. Okay, we want to be able to do this with any parent function we're given. The next one is a square root. So we don't use parentheses. We're going to use that radical symbol, but same process, leave a little space and extend that so there's room for stuff underneath. So this one has a 5x, so we would change it to the reciprocal. That's 1/5 with our x. And outside what you see is what you get. We keep that 4. Now this poses a little bit of an issue. Some of the parent functions are going to be easier to simplify than others. The issue with this one is we're ending up with what happens to be a fraction underneath a square root symbol, which is not really okay for us. Now if you prefer, you can rewrite this as, just like we were talking about fractions earlier, top times top, bottom times bottom. This would be x/5. And the benefit to doing that is seeing the problem and being able to fix it. We know this denominator is the issue here, so we have to rationalize it. And I like to rationalize it right under this symbol. We want 5 to become a perfect square, so we'll multiply it by itself. And I'm going to show more steps than I normally would here, but just to be very clear, on the top we have 5x. And on the bottom we have 5 times 5, which is 25. And that's where our problem goes away, because this says take the square root of 25. So here's where the extra step comes into play. This 25 was on the bottom, so that's really 1/5 once you take it out. And then we're left with just this 5x on the inside. And then these can be put together for our final answer, 4/5 times the square root of 5x. That's really just about as messy as it gets. Okay. Only have to worry about that when there was a fraction underneath a square root symbol. If it's just a regular number under a square root like 5x, no problems. Let's look at this parent function. We've got 5 to the x, so our parentheses would be involved in our exponent there. So I'm going to leave space in front of this number 5. Okay, but then the number 5, the exponent is where my inside numbers with this 3/2 x go. So I see 3/2. Again, I'm using the reciprocal, so that's 2/3, and just putting the x to the side. Parentheses not really necessary once again. Now, this 7 has to go in front, so here's really where our parentheses are going to come in play. You wouldn't necessarily need them, but I like to write exponentials where the base is in parentheses. Not required. If you want to just put times there, okay. But something that's super important with exponentials, 5 is part of the parent function, which means it has to stay in your final answer. You cannot change this. So this says 7 times 5, but order of operations says you would have to do the exponent first. Since we have a variable there, there is no way to simplify this. So leave it alone. That base of your parent function has to stay in your answer. Okay, couple more here. The parent functions look a little different, but I want you to pause the video and take a stab at them. See if you can figure out where your grouping symbols would be and whether they're necessary or not in your final answer. Okay, so pause the video and try those two for me. Okay, this one, in front here is where our -4 goes. We're timesing by 1 instead of seeing x divided by 5, okay, that's going to be 5 times x. Okay, so a little bit trickier in how you're writing it. If you'd like to write that as 1/5 x so you can see it's clearly going to go to 5, please do that. But I like to think of it just as division, and when we switch division, it changes to multiplication. And then, for this one, that -4 can go straight on the top. divided by 5x on the bottom. Something that's super important here, that x needs to be underneath that fraction, not to the side of it. Okay, it does change the value. On the second one, y equals, that 6 goes in the front, and then we're taking the cube root this time. Instead of 1 at 9th x, we're going to have 9x. Okay, here we've got a root symbol again. This time it's a cube root. So we want to think about numbers underneath. 9 is not a problem because it doesn't have a fraction, and we can't take the cube root of 9 to simplify. There's no perfect cube that goes into it evenly, so this one is good too. We can't multiply that 6 through, just like with our last one, that symbol gets in the way. That is all you have to do for that one. The next few problems we're going to work backwards, and in order to work backwards we have to make sure that we're seeing some sort of grouping symbol to mean our parent function, and then we want y equals to happen. So the first thing we need to do on this part is y equals is not happening because this divides by 7. So we're going to multiply the 7 over, and we know we want to just put it in the front. So that's 7 times x divided by 3 getting squared. Now when we're talking about the rule, remember, we're starting with s of x comma y equals, and then we're just writing a big ordered pair on the other side. So whatever we see with x, we switch, and that number in front goes with y, we just write what we see. So first up, this says x divided by 3. Remember, if we say that out loud, it kind of makes things easier. So we're going to say x times 3, or 3x, when we switch it. If you prefer to write it as, when you move this over, the 1/3 x, so that you know we're going to see 3x, that might be helpful for you. Over here, though, the number in front says 7, so we're going to take 7y to finish up. And that's our rule. It just says all the x values get multiplied by 3, and all the y values get multiplied by 7 when we compare it to the original parent function. This one, we've got an absolute value, so that's new parent function, but the rule does not change. We're going to start s of x, y equals something with x, comma, something with y. So here, because this 5, 6 is inside with x, we're just going to flip that and call it 6/5 with x. But there's no numbers left, meaning that y got to stay y, and there's nothing in front of it. Okay, so there may not be a rule happening. Okay, just leave it the letter x or y when that is the case. Next up, our parent function is x cubed, but we don't see parentheses here to tell us that. Okay, remember, when there are not grouping symbols, you just hug the variable, and that'll indicate what goes where. So to start out, s of x comma y equals, you see if you can finish the rest of this one and this one over there for me. Pause the video and try those for me. Because there was nothing with x, that just stays x, and over here we've got a -8 in front with the y, that one's done. Over here we have to multiply by 6 to get the y equals, and then inside I see 2x. So when I write my rule, s of x, y equals, I'm going to start with the reciprocal of 2. That's 1/2. And then I'm going to keep that 6 to go with 1 by y. And that's it. Now, something I want to mention real quick is negative signs that we see happening here and on a previous problem. When we think graphically about a y value, so I'm just going to pick a y value, say this is 0, 1. Okay, when I multiply that by a negative, that becomes negative. Really, it's 8, but what we're seeing here is a reflection over the x-axis. Okay, we've talked about this a little bit, but let's stop to take some notes here because I think your homework asked a question about this. But when we talk about a rule change that makes x, y go to x negative y, that's a reflection over the x-axis because the x stayed exactly the same. When we talk about a rule that makes x, y go to negative x, y, the x switches over. That would be going from +1 to -1. That's a reflection over the y-axis. Okay, so just like we think with our transformations of graphs from our note card, negatives still mean reflections, but talking about that ordered pair, it does switch. If you're talking about the y value, it goes over the x-axis. Talking about a negative on the x value, it goes over the y-axis. Okay, so just to mention that to help with your homework. We've got a couple more problems here. I wanted to do these ones together because it's a little bit tricky on keeping stuff organized with fractions, and I wanted to explain what was going on over here with the weird notation. So first up, same process as before, we got to get y equals. So I'm multiplying the 3 over, and I've got y equals on the top. Just going to multiply straight across. I have 15, and on the bottom I have 4x. Remember that the parent function is wherever the x is. So x is in the denominator, that 4 gets grouped with it. So when I write my scale change rule, I'm going to say instead of 4x, I'm going to say 1/4 x. It doesn't matter that this really was a fraction where 4 is in the bottom. My grouping symbol for my parent function says x was supposed to be on the bottom. So that 4 is a 4, and we flip it in our rule. Then 15 is on the top. Okay, that's the same as saying 15 times the parent function 1/4x. So it's instead of in front, it's on top, but it's still a regular 15, so our rule says 15y. Okay, so that's a little bit tricky, but keep in mind with our hyperbolas or with our inverse squares, the number in front often shows up actually on the top of our fraction instead. Now, what's going on over here, notice you'll see f of x. That just represents some sort of parent function in general, but we're going to use this notation a lot of times when we talk about graphs that don't have a specific shape. So instead of being like a parent function that's traditionally one of the ones we know, our square root, our absolute value, our quadratic, things like that, it's just a random graph of points. So a random graph of points will usually use this just plain f of x instead of a specific equation, because sometimes we can't make equations for particular points. So the process doesn't change. We still want y equals. So multiplying by 3 over y equals -3/4 f of 7x. These ones are almost easier to work with because it clearly shows you where the parentheses are, and outside is dealing with your second part there. So y, or s of xy equals, first we go inside with 7x changing to 1/7 x, and then what we see is what you get on the outside, so -3/4 with the y. And that's it. Okay. While we're speaking of weird graphs, this is kind of what I was talking about. They're using this f of x to talk about this weird graph. It's not a parent function, it's just a function because it is a collection of points that does pass the VLT. So what we're going to do is graph the translation or the transformation of this using the scale change. Now, in order to do this, we want to come up with the rule because rules directly relate to the graphs, whereas the equation has the pieces that are backwards. So what we're going to start out with is finding the rule. Same process as before. Get that y by itself. 3 goes in front. So inside I would have 1/2 x, and outside I have 3 that goes with my y. And from there, we're going to make a table of points. So you've got a bunch of space down here. We're going to make a table, and instead of having an x value, we're making a table of points where the first column are the original points, x comma y, and the second are the points using the rule, kind of like that activity we started with. So 1/2 x goes first, and then 3y goes second. The first column comes directly from the graph. Okay, so pause the video and just write down those ordered pairs for me. -6, was A, and it might be good for you to actually put A to the side. And then B was -2, -2. Okay, then we've got C being 0, 2, D being 2, -3. And finally, E was 6, -3. And once we have those points, all we have to do is take all of the x values, multiply them by 1/2, all of the y values, and multiply them by 3. So let's do it. If you remember from geometry, transformed points usually get this prime notation. So I'm going to use a prime all the way through e prime here. So taking half of -6 is -3. 0 times anything is still 0. First point is done. B prime, we've got -2 times 1/2, so that's -1. And -2 times 3 is -6. And that's done. Okay, what I want you to do is pause the video and find the last 3 for me. All right, hopefully you got 0, 6, and then 1, -9, and then 3, -9. And we'll just go plot those points over here. -3, 0 gets to be our A prime, and you do want to label that on your picture. -1, -6 is our B prime. 0, 6 up here is C prime. 1, -9, D prime, and 3, -9 is E prime. So because we had a situation where these were just scaled, they weren't reflected, this scale change should preserve the shape of it and the orientation. Okay, so which letters connect to each other does not change under a scale change ever, meaning from A to B, you're going to connect A to B the same way, B to C still gets connected, C to D, and so on. Things that can change are size, obviously. When we're scaling, something could get bigger or smaller, but also you could have a reflection, so the order of these points necessarily wouldn't be the same pattern, so wouldn't go down first necessarily. Okay, so we do want to connect them in the same manner, though, using a straight edge because we started there. That is our transformed f of x. Last couple questions are how we can apply scale changes. So first step, 14 says find the scale change s. That tells you automatically your answer should look like s of xy. And it says that stretches a graph horizontally by a factor of 4 and shrinks it vertically by a factor of 1/5. Okay, so we're talking about some graph, some f of x, and horizontally we want to go by a factor of 4. Horizontally means we're going to change the x values. So our x values get stretched by a factor of 4. We're just going to say 4x. Okay, the second part here shrinks it vertically by a factor of 1/5. Okay, with the rule, it tells you exactly what happens on a graph. That's why we had to, on that last problem, find the rule first, because what you see is what you get on a graph. Then the equation kind of says it backwards. So we are just writing what we see here. This 1/5 stays as well. Okay, so for a rule, matches the graph. And the same thing happened with translations. Okay, if you wanted to go right, you had to add. If you wanted to go up, you had to add. It says the zeros of a function are -12, -4, and 8. Zeros is another word for x-intercepts. So we know these are points. Then it says the y-intercept is 16. We want to give the new x and y intercepts for the image. You can do this the same way you did the last graph situation. You can make a table. So xy is going to 1/4 x, -2y. But it's really as simple as thinking about if these are x-intercepts, these are x values, so -12, -4, 8, and intercepts have 0 as their y value, meaning these are going to stay 0. All that's going to change is the x gets multiplied by a factor of 1/4, so this would be -3, -4, and 8. And then our last one was a y-intercept, so the y value is 16. And that means that 0 stays over here, but the 16 gets multiplied by -2, which is -32. So your final answer are the points -3, 0, -4, 0, 8, 0, and 0, -2. So this one you don't have to make a table if you can see ahead on which part of the rule you're going to use, but you do have to write those as ordered pairs because when we're talking about intercepts, they are points. Okay? If you have any questions as we went through this practice with the examples, please come in to see me.